The broadcast is now starting. All attendees are in listen-only mode.
Hello and good afternoon, everyone. My name is Anna Zylik. I am with ICF, and we are the vendor working on behalf of the sponsors of Energize Connecticut to bring these passive house and all electric homes trainings to all of you. So thanks for joining us today. These trainings are at no cost thanks to the sponsors of Energize Connecticut and are part of a partnership with Connecticut Passive House and Build Green Connecticut. Today's training will be recorded and will be available online afterwards. A quick reminder that as part of this training and workforce development initiative, we are offering a 75% cost reimbursement for individuals pursuing either FIAS or PHI professional accreditation. So this includes the cost of the trainings and the exam. And once you become certified, we'll work with you to process the 75% cost reimbursement. So if you have any questions about the reimbursement process, please do not hesitate to contact us. With that, I will pass it over to Keegan Ebbets, who's also with ICF, to talk about the Passive House and All Electric Homes building incentives.
Thanks, Anna. And Jonathan, if we could go to the next slide. Hi, everyone. Excited to have you with us today. Thank you for joining. So in addition to the no-cost educational webinar series and the professional accreditation reimbursements, the sponsors of Energize Connecticut also offer robust incentives for builders and developers who choose to go all electric with their residential buildings or pursue passive house certification for multifamily projects with 5 units or more. The Passive House incentive design for Energize Connecticut is shown here and includes pre-construction incentives for feasibility studies and energy modeling and post-construction incentives for full Passive House certification. The all-electric incentive, next slide, is for both single-family and multifamily buildings. It offers 2 levels of eligibility with specific design and performance requirements associated for each, and has incentive amounts ranging from $1,500 a unit for multifamily up to $10,000 for single-family homes. Our goal ultimately is for everyone involved in the construction of residential buildings in the state of Connecticut to be aware of these incentives. So if you are interested in learning more, please visit our website or contact us directly. As for questions during today's session, please feel free to use the chat function on the GoToWebinar control panel throughout today's presentation, and we will relay them to Jonathan. And as a reminder, this training was approved for AIA CEUs. So if you're interested in recording those CEUs, we will follow up with a notification out to everyone who attended today after the presentation. And with that, I will turn it over to today's presenter, Jonathan Hernandez from Brightcore Energy. Jonathan, thanks so much for joining us.
Thank you very much, Keegan. So welcome to Geothermal 101, I like to call it, a little quick crash course. I'll have an agenda, and then afterwards we'll open it up, hopefully, to questions and discussion. And as Keegan mentioned, feel free to use the chat throughout the lessons. And the idea here is to have some sort of free-flowing back and forth. This is a sophisticated audience that understands building science and the value behind geothermal, so there's no such thing as a dumb question. All right, so let's get started. The agenda will basically be 4 main points. It'll be an introduction to us, Brightcore, very briefly, just so you understand who we are and you know, why are we authorized to have this kind of discussion. And then secondly, after that, basics of geothermal. We're not going to go into heavy thermodynamic equations, but we will discuss how systems really operate with the building itself. We'll discuss the difference between surface systems and subsurface systems, and also how the IRS looks at these systems, and then some of the more innovative things that can be done with these systems. After that, we'll get into discussion of considerations. What specifically goes into these types of systems when it comes from surface considerations, subsurface considerations, space constraints, permitting, etc. And then finally, the last big section will be innovations. And what I mean by this is there's a technology that is far more common overseas, specifically in Europe, where we're talking about thermal energy storage. Now, you may have heard of various types of thermal energy storage, whether it's battery form, hydro form, molten salts. But what we're talking about here is borehole thermal energy storage, BTES, you may have referred to. And we have an example here on the North Atlantic coast that we did specifically as an innovation project and proof of technology and proof of concept stateside. So that'll hopefully open it up to a lot of discussion, everything from building science to borehole drilling and everything in between. Fantastic. All right. So Brightcore Energy really started almost a decade ago with lighting controls and specifically on efficiencies for buildings. So it comes from a place of trying to make buildings perform at their peak efficiency. One, because there's a fight on climate change, but as policy caught up to the technology, there was impetus to kind of really diversify our services. And that's when Brightcore recently got into geothermal in the last few years. The Inflation Reduction Act had a big portion in that, and we've grown. We've grown to about 120 employees. We serve the North and Midwest Atlantic states. But most importantly, if you notice at the locations, as an energy service company, we have both our headquarters for brain power in Armonk and in Brooklyn, but Rock Tavern is where we house our own equipment. So when I'm talking to you about drilling operations, I'm not talking through a lens of subcontracting someone. I'm talking through a lens of my own personal experience in the geothermal industry, but also Brightcore's experience on how these systems really are installed and what is considered as a developer. And then finally, our Stockholm, Sweden office is where we are able to innovate in our modeling efforts, which is critical on sustaining these thermal reservoirs. You really have a base load solution akin to the geothermal power sector, where it's 24/7, always available and always efficient. So that in mind, that's where geothermal and Brightcore kind of met as a nexus. So as I mentioned, we have various services. Today, we're going to be discussing specifically geothermal. And what came about was this market imperative that the HVAC footprint when it comes to greenhouse gas emissions, especially out here in New York City or other large cities on the Atlantic coast, is due mainly from the heating loads, but also from the sources in which those heating loads are satisfied, right? Specifically fossil fuels. With legislative and regulatory mandates, as well as ESG goals, electrification has become the lowest hanging fruit. And when you look at HVAC and electrification of HVAC, now you're looking at considerations such as CapEx, OpEx, and really an impact to electrical infrastructure, both as a consumer, but also as a member of a grid altogether. So if you notice, plugs, lighting, which we've done, and then hot water and HVAC are two things that can be addressed by geothermal. Oh, pardon me. So when we're talking about electrification, well, then we're talking about, look, all right, if I'm going to electrify, great, I'm sacrificing a gas bill for a higher electric bill. Well, not necessarily. So the key here is then COPs, coefficient of performance. Some of you may already be familiar with this concept, but essentially what it means is that 1 kilowatt of electricity, which we see on our bill, depending on where we live, cents per kilowatt hour, can then be transferred to become, through mechanical energy, into thermal energy, whether that's air source using ambient temperature outside or ground source, geothermal, using the bedrock below you. And those are both more efficient than your electric boiler or your classic fossil fuel heating system. And I don't mean 10%, I mean by 2 to 3, in some cases 5x the efficiency. The efficiency can be at peak seasons, because in HVAC there's 2 seasons, not 4. There's peak seasons, hot or cold, and shoulder seasons. And that's how architects and building scientists and we at energy management type companies and developers think as well. So when we talk about the market imperative to electrify, we talk about the solutions that exist and maintaining that core, I think, industrial scale vision of being most efficient, ground source stands out. What does it mean in terms of a business case? Well, ground source, when you're looking at replacement cost and the OpEx, those are really the winners. The energy costs also decrease depending on your load, but the geothermal post incentive at the first cost is also the largest. And what I mean by that is that a ITC, which we'll talk about as well, can give you 30, 40, or 50% of the system cost, not just the ground system, but also the surface system attached to that ground system. And we'll talk about that in specific. So I've thrown a lot at you. Don't be shy about the questions as we go along, but this is really how we got into geothermal as a company and why it makes the most sense, as I'm sure you all know, when you're talking about passive house and being efficient as a building. Well, now your energy sources are also working towards that efficiency, so that it's a symbiotic relationship. Specifically about policy and how to promote these are the incentives I mentioned earlier. So one of the key things, if you see the 5x multiplier, but there's also an added, I guess, almost a moral imperative when it comes to an energy community adder. These are along the lines of environmental justice and equity as well, which is a big part of the geothermal industry, whether it's underrepresented communities having access to the same high efficiency. In New England, there's a great nonprofit called HEAT. They have this wonderful story of the last grandmother. And essentially all these people along the gas grid, for example, have the capital to go into lower efficient electrification solutions. But this last grandmother at the end of the grid is going to be paying for the entire distribution on her own. And that's why it's important to have visibility when it comes to energy community adders. So just something to contemplate. All right, now we've gone over Brightcore as a company and geothermal and our vision. Let's go over some basics on how these things work, why they work, and we'll get into some fun geology later on as well. So we go by a very basic workflow, and this is very common in all energy sectors, whether fossil fuel based or renewable. But the idea is feasibility, then you go into the design and development aspect. But then what makes this different is that it's not a one-off building, it's constructed, let's move on. You have to take care of this system, similar to geothermal power. There's a reservoir of energy that needs to be exchanged and maintained. And that's key, and I want to make that clear. Exchanged. Power is not generated. Energy is exchanged, which is a different animal altogether. So when we talk about 1 kilowatt in to produce 3 to 5 kilowatts of heat, it's done through exchanging bedrock temperature, okay? And what does that mean? Well, that means that in winter or summer seasons, as you see here on the right, those are the peaks. Now in Connecticut, winter can be pretty cold. Let's call it freezing, right? 32 Fahrenheit versus bedrock that is significantly warmer the entire year. That warmth comes from all the way from the core, really, of the earth, and radiation and heat basically flowing through rock on its way to the surface. Bedrock, similar to the formations that are found, for example, in Connecticut, where you have metamorphic basement, which is very dense and sometimes permeable along certain fracture networks, but overall, it's a pretty solid chunk that you're sitting on. What that means is that temperature can maintain itself in that high density rock through what's called thermal conductivity, or capacity, really. In the summer, it's so hot that bedrock seems like a cooler option. Pun highly intended. And the idea there is that you will always have an advantage in these peak seasons to exchange. I got too much heat in the building, let me throw it into the bedrock. Oh gosh, there's not enough heat in the ambient temperature, like an air source heat pump. Try finding heat in a blizzard for an air source heat pump. It's going to work harder than it should. But the bedrock has that access. And that's how heat exchange and ground source heat exchange systems actually work. But they only work if they're connected to the building system. Now go to the left side. So the green is what I've explained. The blue is who benefits, right? So what happens here is this is where the energy, depending on the season, is exchanged to and exchanged with. So there's a cold intake, heat return, or vice versa, depending. But what's nice is that it can provide cooling in the summer as well as heating in the winter. Now, I know the word geothermal implies heat, but that's really what it is. It's a thermal difference, and that's the key here. What does it look like when we talk about design? Well, one of the nice things of that last slide is it shows that the bore field is directly under a building. Now, when we're talking retrofits, that's got a set of considerations in itself. When we're talking about new builds, it can be built first with a foundation laid on top. And that's what this example is here. So I also want you to understand that there's a difference between various loops connecting in a way of circuits, which you'll see here. The yellow is a typical circuit. In this case, 5 or 6 boreholes all the way up to 10 or 12 boreholes, depending on the size of the system. And each borehole in the blue is designed to reach a specific capacity per unit. Now that depends on the geology and on the depth, the type of load that we're looking at. And then on the green, you'll see where all of these circuits lead up to, and that's the manifold. Ideally here, probably in a mechanical room, maybe a vault that'll be built within the system. But the boreholes can be drilled and maintained and installed with the building. So after the cement is poured and you've got your foundation and everything's looking good, you have to go back, recheck, reflush, and test, pressurize, test each loop to make sure that everything that was installed has not been affected by the construction process. It's something that has to be scheduled in, and that ideally will not cause a delay because it'll be a parallel activity to other operations in the building, of the construction of the building. So that's one system. Another one, for example, and that was plan view. If we look at another building, side view, now you're looking at individual units. If you look at the first floor, blue circle, bottom right, or blue square, those are the high density polyethylene lines. That's what it looks like coming out of the ground and leading into the building. Once it's gotten to the building, to the top left, you've got the boiler room, for example. That's where it can interact with the building system and use something, for example, like a multi-stack at each closet or however it's set up. So it can be both a system that can be retrofitted or a new build. And these are really good examples on how these things kind of look from a design stage. And this is not a typical water well. Let me drill a hole and install your pump and thank you very much. This is an entirely symbiotic system within the building HVAC system that requires this level of engineering and design, in our opinion, and is best practices really in the industry. Now, these are, I've only discussed fully geothermal systems, for example. Well, there is a space sometimes where a hybridized system is really, really what the client would best benefit from. And what I mean by that is peak efficiency, as well as trying to be efficient on managing waste heat altogether. So here you have a air source heat pump within a heat exchanger of the loop that connects to the geothermal boreholes, but also a heat recovery chiller. And it's a 6-pipe system. And what this also can allow is for air to air, air to water, as well as providing a source. Let's say in the winter there's excess heat because the building is so gosh darn efficient, like in Passive House. We can capture that heat, put it back to the bedrock for a rainy day or a snowy day, and or be able to transfer that energy when efficient to help in the step up of, or the lift of domestic hot water, for example. So there's a lot of flexibility when it comes to how that heat can be transferred throughout the system. And there's our larger systems that you know, we're talking thermal energy networks, district heating, where you can do ambient loops, we can do central plants. Geothermal really, after the borehole, when it comes up, is a lot of mechanical engineering, creativity, and cooperation with the building engineers and or facilities management team. So that's something that's very, very important, because these systems, like I said, are long-term solutions that need to be carefully crafted, as either the building loads will change over time, the usage of the building, and these systems are designed to last 50 to 75 years. This is high density polyethylene with high quality thermally advanced grout. They've got specific chemical compositions that allow for increased thermal conductivity. So these systems will outlast most of us in our careers of 50 to 75 years with proper O&M, which is still the lowest cost compared to its competitors. So geothermal makes a lot of sense, and these are some of the basics on how we design, well, not design, but how these systems are installed. And one last thing before I jump too quickly. On the left, that blue and green, that is a full geothermal system. Bore field is nothing without the mechanicals, and a mechanical field is not a geothermal system if it's not attached to a ground loop. That's how we see it. That's how engineering sees it. That is how the IRS sees it as well. Meaning that if you're going to install a ground source heat loop and you're doing Division 23 mechanical engineering work on the surface to a building that is attached to that loop and will be serviced by that loop 75% over the full year, that is also will qualify for 30, 40, or 50% from the incentives available. Okay, the considerations. So now you see what they look like, how they're installed, how they interact with the buildings, and really the nomenclature behind. We're going to get into, well, what's a good candidate look like and why? So when we begin a lot of these feasibility exercises, we really need to look at what is the target load and what can we actually physically install. And you can get creative, and you'd be really surprised on the amount of energy that is literally beneath your feet that is accessible with just a little creativity. So two typical types of systems. There's a U-bend, and that's the one on the left. That's your standard classic. It's high density polyethylene like you saw in the photos, but pretty standardized depths. For example, recently, last year, 499 feet was a pretty typical depth, but not because of any thermodynamic limitation. It was more administrative. Mining permits usually were required if you were going to be drilling deeper than 499 from whatever commission happened to have that authority. However, there's two big differences, and I'll start here. On the left, you see that I've never really said the word well. We are drilling, but we are creating bore holes. Now, engineering-wise, to create these things, it's very similar. You have a drill rig, you have your drilling fluids, you have your cuttings, you've got your geologic considerations, etc. But the final product really is a large column, and by large I mean maybe the size of a basketball hoop, and large really the depth of 85-story buildings all the way down to 850. And the idea is that it's a loop inside of a grouted column. Therefore, the grout A protects the loop from any lateral forces within the subsurface, but more importantly, perhaps, it isolates these loops from potable aquifers, which after administrators realize this, that it's not a well, you're not interacting, you're not injecting, and you're not pumping. You are basically an independent system installed within the matrix of the subsurface, meaning that you now can go beyond 499 and not require a mining permit because of the non-invasiveness of the technology. Previous generations of the technology did use water wells. And at the time, it worked for the most part. However, water tables are fickle beasts, and as you develop an area, you know that water table is going to go lower, which creates higher demand on your pumps, which increases your electricity bills. And I'm probably talking to people who've heard these horror stories in the past. That is no longer the case. With a closed system, A, no aquifer dependency, but B, there's a known finite volume and a known finite distance and cross-sectional area, so now you know what your pumping capacity will be over time, over the long term. It's a known value, no longer a variable that depends on hydrogeology. Okay, so that's your typical U-bend. There are some occasions where site constraints are so tough that you may have to drill a larger hole and put two loops in one hole called a quad loop, just so you know that in case you come across it. We are experts in that as well. And then on the right is a high performance heat exchanger, a coaxial exchanger. So instead of a U-bend, this is a coaxial, right, concentric tube inside of a tube, really, system that allows for turbulent flow, which dissipates heat quicker, meaning you can access more tonnage per hole but the hole is deeper. Now, this is done with woven glass and specific type of material that is not high density polyethylene, but it is a high performance heat exchanger and has been installed already in, for example, Massachusetts at the famous Jenga building, the Boston University Library. Any questions thus far? Even if it's just for me to catch my breath.
Hey, Jonathan. Yeah, there's one question. Are there different types of grout for closed systems, and what is the heat transfer characteristics?
Good question. Yes, there's a standard grout that is used unless a specific condition is required. Typically, I've seen thermal conductivity tests. So aside from the grout, those tests also measure the effect really of the subsurface on that grout. So it's kind of hard to say, but I'm sure lab testing, they give you probably a minimum of 1.2 BTU hour type of conductivity rate. Some tests come back 1.4, as high as 1.6. So that's on the average, per foot, 1.6 BTU hour per foot. That's pretty good. 1.2 to 1.6 is a good range. I'm comfortable with broadcasting. When it comes to Rygans, they're higher. So it's something, I've seen 1,000-foot Rygans where you can conservatively get 8 to 10 tons per borehole, as high as maybe a dozen. There's still a role for subsurface to play in how effective the grout can be. Did I make that clear enough? I hope I don't want to, try to dilute the answer, but that's probably the best way to explain it.
Yeah, we'll see if that individual has any follow-ups. Two other questions, Jonathan. Can geothermal be employed at coastal locations?
So there are in Long Island, for example, there are geothermal systems going back decades. I know in Cape Cod, we are led by two of the most brilliant minds in northeastern geothermal. And what's great is that typically these two people would work in silos and not with us. We're very grateful for that. But Dave Hermanton, who's a guru when it comes to engineering and designing of these systems for a long time, going back to the water well systems, has told me stories, as well as Tracy Ogden, and she's out of New England in Ogden Drilling. She's drilled tons of these systems out in coastal regions, up and down from Long Island up to Massachusetts. So yes, the one thing I will say, and I'm not a design engineer, but subsurface wise, coastal regions have more unconsolidated, let's call it loose sand, gravel, silt, rock, which reduces density of the overall subsurface thermal mass. So you'll get probably rapid equilibrium. It'll try to get that water offshore, washing away heat. We'll get it back to its temperature not, right? Let's call it 60 degrees. But storing it for a snowy day is a different beast altogether. And it's a little bit beyond my scope specifically, but we definitely have the minds and the tools to find out exactly. So that is where B-Test, being a new technology, meets its match in coastal subsurface terrain.
Great, thanks. A couple other questions, but maybe we save these others for the end if you want to keep moving along right now.
Perfect. Yeah, these were great questions, by the way, and I hope I've answered them. And if not, chat's open. So we'll move on. These are the two systems. Now we're going to get to the drilling. Specifically, Brightcore, we employ three types of rigs for three types of operations primarily. On the left is your classic, what we call truck-mounted rig. Usually you'll see with water well drilling. These rigs are larger, but are more mobile. They can get on off roads. They can, set up on uneven terrain and even themselves out with their own landing pads, essentially. And what's nice about these rigs is that they can be set up fairly quickly and demobilized fairly quickly. We use them a lot in thermal conductivity testing of test holes. So in most drilling operations, you will drill a test hole. Even if it's your first hole, it's still a test hole because no one's been down there at that exact spot before. These are great for that. On the right is now when you see track-mounted rigs, and these are GTD 350s, very common in the industry. What we have, though, is we've used these systems very successfully on doing multiple boreholes in multiple rigs. They're smaller and have track-mounted that can be in construction sites and have great pivot rotation, which make them able to do multiple boreholes with minimal movement. So they're very efficient when it comes to drill rate, whether it's boreholes per day or feet per hour as well. They've got strong pumps. They can do water, air, and mud. So that's key. And then the very far right, we're really proud of this. We've taken off-the-shelf technology at Brightcore to do retrofits. This opens up a whole new market. And what this allows you to do is go into basements of buildings. This is an example of one. And it's mining technology where they have very limited space, have to be very quick and very accurate when you're looking for a gold mine, literally in the side of a mountain. And that's the technology we've used to do smaller, quieter, quick, and deep drilling in tough areas to reach. One of that things that we have here is these are actual pictures from New York. And this is an innovation technology project that we did last year near Central Park. And that'll be some of the results that'll be published, I believe, next year. And it was done through NYSERDA. But there's a lot of innovation interest in doing these types of things, especially in retrofit markets. So just something to consider, and that's something that the industry has always been looking towards. When we look at projects, let me get back to considerations. When we look at projects as a whole, we look at them regionally, as you see bottom left, the geologic maps of the area. We look at known infrastructure, whether it's water tunnels, subways, and then bedrock geology. And just because you've hit bedrock doesn't mean you've hit what we call good bedrock. There's weathered bedrock. And in our system design, we need these things in order to conclude our feasibility analysis and really drill down to what the building needs, but also what the subsurface within the lot can provide. Some of the examples of how advanced some of these systems can be, but I'll go over a very simple example in the next slide. There we go. So you may have seen tricone bits before, but how they actually work is you've got spinning cones on a spinning device. So you've got several rotational spins that can create torque. Anybody who tells you that they can drill a perfectly straight hole, ask them for their snake oil too. Might as well. No, it's really hard to drill a perfectly straight hole. Any driller worth their salt will tell you as much. But you can mitigate these things, and you can be fairly accurate. But it's basically due to these conflicting moments and forces that are affected, whether it's a water table or aquifers or various formation differences. But this is the overall general idea. And what that does is it allows you then to drill through unconsolidated with that bit and heavy mud to hold back these unconsolidateds until you hit bedrock. Now that depth to bedrock is important because that's where we drive in casing. That casing then is like when you dredge a river, right? You build dams all around so you have access now to the subsurface without the need of stuff getting into your project area. No different. Unconsolidateds are held back by steel casing, driven into good bedrock, creates a seal, and now you have an area to work in through the bedrock. You may hear from people, bedrock's really hard to drill with. Well, nothing's hard if you have the right tools. And that's what we employ with whether it's air hammer, water hammer, PDC, which is poly diamond crystalline bits, which work really well in these tough metamorphics. Schist, granite, gneiss. You've got shales even that can be kind of hard. These are indurated metamorphics that have been around for hundreds of millions of years. And so you got to pack quite a punch to get through them, but it's definitely doable at a commercially scalable rate. Once you get through this bedrock and you've reached your depth, and based on your testing, you know how much tonnage you're going to get, you run your loop. This is a U-bend loop, schematically speaking, and then grouted from the bottom up. That grout will then displace by higher density all of the fluid that was holding that borehole open, whether it was water or mud. If it's air, there's not much to displace. It's typically water in the water table. and that grout displaces that, and you are now left with a perfectly, ideally grouted column similar to a soil nail in a retaining wall. You have this high density column within the matrix. Over and over again, you can create a field. Now, this is a typical vertical bore field. Spacings can vary depending on how much tonnage. There's some specific interference the closer they are bunched up together. That is how we design them according to our numerical models. Pretty advanced, and they have 4D, which is really a transient system. It's how does it react in XYZ space over T? And you need that because T changes, little t time, but also delta T outside, peak seasons, shoulder seasons. And so all of that has to be modeled over at least a year to give you really what the system is going to look like on a cyclical scale. We have all these loops then either connected through circuits, as I mentioned, and expanded every which way. Now, let's say you don't have a lot of area. Well, you got to get creative. So as I mentioned earlier, mining, for example, typically does not drill straight. They drill at angles into the sides of mountains. So incline drilling is a known technology with very little risk that we know how to do. The industry. All three of those rigs that I showed you can be inclined at surface to do angle drilling. On the left, you see a smaller surface area impact, but a large thermal volume accessed, much larger than you would from conventional drilling of a bore field. On the right, you go to the far right, that green rectangle is a 60,000 square foot lot. And you can fit about 138 boreholes in there at 21 feet of spacing between, right? The same amount of boreholes, the same amount of loop can fit on 25,000 square feet, less than half, and access the same amount of, well, a larger surface area below, but a larger thermal mass than it would fully conventional drilling. So you really achieve the same goals by reducing your surface impact through these types of systems. And a real world example in Connecticut, funny enough, is as follows. You're given a path in a well-developed area, and you have to say, hey, what can you do for me here? Now, conventional thinking, as you saw in that previous green square, will mean vertical boreholes drilled at specific distances. Let's say you can fit 20. Now, if you bunch them up closer, but you angle them out, you can fit much more of thermal mass and loop into a system, meaning that same bike path can now turn into the equivalent of a rugby field to acquire the energy and exchangeability for your project. Now, side view looks like this. You've got 1.5, 4.5, 7.5 degrees from the vertical, and you can hold that with those drill rigs, as I mentioned, and really increase your capacity while decreasing your surface impact. And that's important. When you look at this, you see telecommunication, gas, water, electricity. There's a lot of headaches to be avoided, but B, there's an aesthetic thing to this. There's, we are green drilling, and typically that means low impact of all kinds. And so the more compact our systems can be at surface while still accessing the same energy is a win-win for everybody across the board. And this just, for architects and for users of the building, I mean, it's a win-win overall. That system grew to be this system. You may be able to see where some of these, where the path was and splayed out, and it evolved. And it evolved into a bigger project that is now a thermal energy network. So you've got multiple systems talking to various plants that then talk to each other. And so if some place has a heat to give and another place needs it, it can be exchanged through a full network. So, if you think back to having your own computer, and then when the internet was born, now you can have a local area network, and now we have wide local area networks, and the networks continue to evolve and become more advanced. Therefore, the systems do as well. Okay, so now let's get into innovation. We're going to combine everything we've learned here. So this is a project that was done for thermal energy storage. Now remember, thermal energy storage, requires typically high thermal conductivity and capacity, which means usually higher density rocks. Well, a lot of skyscrapers were built on a very famous high density rock in downtown New York, which would be the Manhattan schist, part of the famous metamorphic spectrum that you see in the North Atlantic states. But the idea here was to see, can we store waste heat from the summer into the bedrock, and can we access it in the winter through a ground source heat pump, just like you said, these white papers have been showing for 30 years and projects have been showing for half a century in Scandinavia, for example. And NYSERDA said, have at it, let's see it. But to add the kicker, it's going to be a retrofit in a very old building in the basement in Manhattan. Go. And we did. We were able to really prove, the concept of retrofit buildings for geothermal in an urban landscape, borehole thermal energy storage, incline drilling, minimizing surface, maximizing subsurface, in a very well-developed subsurface area, whether it's a subway or water tunnels or just general infrastructure. And it was pulled off pretty close to design in general, but what was accessed was enough to create the proper thermal energy network, or I'm sorry, thermal energy storage system. What that really means in numbers, now this is not, that building was called the Beresford. This was not the Beresford. This is a project that was done in Scandinavia and Sweden. But what I want you to keep track of, we're all data scientists really in a way here. We love data. So here's real data. If you look at the outdoor air temperature, which is blue, January 1st in Sweden, you can imagine it's pretty cold. It's freezing, literally about 35 F, fluctuates throughout the winter and slowly climbs to about 75, 80 in the summer, July 1, and then it comes back down. So you have a sinusoidal, cyclical, ambient temperature system that you're kind of focused on. The reason is, well, in these peak seasons, now you have the temperature to the B-test, which is the gray, and the orange is the temperature from. So the temperature in the loop and the temperature from are pretty similar in the peak season, which make it pretty efficient, but it's far different than the outside temperature. But then as you get to the summer, you notice that your temperature from your B-test increases. Yes, it goes up to about 60, but it's still far cooler than the summer outdoor temperature and the ambient temperature that you're working against. But then you're able to bring it right back down to position not on New Year's Day the next year. And that is what makes cyclical and thermal energy storage a key component in peak shaving, in overall greenhouse gas emissions, but also satisfying the IRS of the system always contributing to try to hit those benchmarks so that you get full ITC. And that's where thermal energy storage is a game changer. Typically, geothermal is associated with rapid heating or rapid cooling. Thermal energy storage can take advantage of what was considered tougher rock to drill, tighter spaces to drill, and satisfying a market that is urbanized or so developed that it could really use any kind of help it can on the grid. And that's what this is about. There's a energy efficiency, but also an energy demand response on behalf of the geothermal system to the grid, as well as to the building. So I hope you guys have learned. I hope there's some time for some great discussion and some questions, and let's get it going into the questions and discussions. And I want to thank you so much for your time. Here's some of my contact information, and yeah, Keegan, take it away.
Yeah, Jonathan, we got a few questions in here. Can you talk a little bit about geothermal application in retrofits, specifically multifamily apartment buildings?
Yes, great question. So specifically, multifamily housing is a great candidate, number one, especially with passive house. Should I go into that route or just multifamily in general, Keegan? Was the question specific to passive house?
They don't specify, so maybe a little bit of both.
Cool. So the leakier the building, the more load, especially peak load, because these systems have to be able to absorb that peak load. The larger the bore field, right? The more tonnage you're going to need. So multifamily houses usually, if we're lucky, have some good green areas to drill in, usually some basement areas that can be considered. Retrofits, for example, our smallest rig can do about 9.5 feet clearance. So if you have 10-foot clearance and enough turning radius or an elevator shaft, you can let us borrow for a half a day. We can definitely get drilling into retrofits of multifamily housing buildings. The Beresford was a co-op, but it was primarily residential. That's one way. The second, I think, most important parameter on multifamily housing is how you're going to be retrofitting the system within the building. So if you have end-of-life boilers, if you have end-of-life furnaces, that's one way to where, without moving tenants out, and if you have a specific system that already works with the proper distribution to the units, you can do this without having people basically be unhoused or inconvenienced in retrofits. And that's something we really saw at the Beresford, for example. People didn't know we were drilling. Mike Richter, our president, well-known guy in New York and among hockey fans all over the world. But he went down there and somebody asked him, hey, when are you guys going to start drilling? Mike told him, and it was true. We've been drilling for about a week and a half. And this is a business right above on street level, below the residence towers. And they had no idea. So I think for multifamily housing, geothermal is a pretty uninvasive way to electrify, given that the system is already moving that way. Secondly, multifamily housing is usually larger than what is already in most people's earmarked legislation for carbon footprint reduction. We're looking at buildings that are well over 50,000 square feet on average, I would say, maybe some more towards 100,000 square feet of aggregate gross square footage. And those are going to be, whether it's ESG goals or penalty avoidance, big candidates for this. Therefore, there will be assistance for this. And that is another consideration, I think, in retrofit multifamily housing. There's a huge market for that. Passive house specifically, humans give off a lot of heat. And the tighter the envelope, the better. And not only do you require less load, but you may have extra heat to work with. And that's always fun when it comes to moving heat around a system. So there's a lot of things to be considered in multifamily.
Similar to that, another question here is additional considerations might there be for looking at multi-building centralized systems on a university scale?
Yes, thermal energy networks are kind of the I would say the star of the show thus far. When I'm talking about Department of Energy, Geothermal Technologies Office, state fundings, just in Massachusetts alone, there was funding for various municipalities to do their own thermal energy networks, which is, we're talking campus scale, whether it's a hospital, a university, a small municipality center. These systems, couple of considerations. Number one, you're looking at a larger bore field or set of bore fields. By definition, a network is either 2 bore fields to 1 user, or 1 bore field to various users, or various bore fields to various users, but it's not 1 to 1. It's 1 to 2, 2 to 1, or 2 to 2, right? And when you come to this type of scale, I'll give you a great example. Colorado Mesa University, they have an ambient loop, very well known, been around, NREL, National Renewable Energy Lab, from the Department of Energy, did a third-party audit recently, I think it was published last year in ICHPA, on the efficiency, true efficiency. Their peak efficiencies were off the charts in the winter, and overall a yearly efficiency, I believe, of about 7.5. That's an average over the year. Their peaks were 9, 10 at some points. So at larger scales, you have larger efficiency. Again, it's a closed system. Your pumping power and your parasitic load, as we like to say. And the sky's the limit as you add on. The networks tend to equilibrate quicker because you have more water flow that is always there available as a good ambient loop temperature, but also the smaller system, let's call it a library or a dormitory or a laboratory, those will have interaction with the loop, but won't affect the loop as much as because the entire loop is so large. It's a mass flow / thermodynamic exchange problem, really. And the larger the size, we see gains in efficiency. as opposed to, let's say, one building that may have an average COP of 3.5 versus these large networks that are 7, 9.
Great. Yeah, thanks, Jonathan. Couple other questions. Can you explain a little bit more about how thermal energy can be stored in the bedrock for a snowy day? I believe you called it.
Yes, absolutely. So let me go back to this slide here. The bedrock during the winter in Sweden is about 48 degrees on New Year's Day, which is, I hope you guys can see my mouse. Let me make it to the pointer here. Oh, there's your pointer. There we go. Now we know. So this orange line is your, let's call it your winter bedrock temperature. And because you're exchanging heat, so whether it's through a dry cooler system or through a water-to-water system, that you're able to capture waste heat from the building, you run it through the geothermal loop into the bedrock. If the water that is running through that system, right, has excess heat that it needs to give off, heat will always go from hot to cold. It'll never go from cold to hot. It'll always want to find the coldest place. If that bedrock relatively is colder than the waste heat coming in, you can store it in the summer, as you see here, and increase the bedrock temperature really, because the temperature from the B test, which is this orange, has increased. Because your temperature to the B test, which is this gray, this is you shoving heat at these temperatures, 60, 70, 80. It stays there. You don't see it in the return as much, but it's there. So that when winter begins to come, you'll find that efficiency, and then again, your temp to and your temp from come back to being equilibrated. Especially during the shoulder seasons, there may even be a crossover here at the shoulder seasons. But again, peak seasons is when this mechanism mostly takes place. So you have excess heat that usually you would run through, let's say, a rooftop unit, and just set it off into the atmosphere. You can have that captured through water to air, or water to water, or air to water, and put it into the ground source heat exchange loop. And because just through the residence time of it flowing through the circuits, it will dissipate that heat into the rock, as the rock wants to trap that heat anyway, especially if it's above your standard bedrock temperature. So that's how B-test works. I will admit, it doesn't work everywhere. It works best when you have these cold snaps. Scandinavia, Connecticut. The reason is because if your delta T is large, you are the best deal around as a source of thermal energy, bedrock, because it doesn't change. When your bedrock temperature is 55 and a cold spring day is 55, your delta T is nil, and therefore there's not that advantage necessarily for heat exchange in terms of storage, but you can still have access to that fairly easily at a at a higher COP, at a lower electricity usage. Summer is when you capture, winter is when you reduce. Now loads change over time. And that's why in our systems, for example, we have operation and monitoring, O&M, that essentially tells us that, oh, this year their loads have slightly changed, therefore we need to adjust storage parameters accordingly, whether through the circuitry or through flowing or shutting and off and on, or bringing back valves to create the necessary conditions that adjust to the building loads. So over time, you really want to maintain that sinusoidal balance. You don't want a dampening effect, and you don't want an amplification effect, meaning you don't want to start losing heat to your building, and you'll never lose heat in the rock, but you can be less efficient. And then you don't want thermal drift, where you're pushing too much heat into the rock. Now, rock can take a lot of heat, that all of a sudden now you don't have that advantage in the summer. You no longer have a place to put heat because you didn't take enough out in the winter. All of this needs to be managed with 8760 data. We do our stuff on like 15-minute pulses, so you can imagine the data sets. And the idea there is to monitor it in real time and make the adjustments in real time. Because, as I'm sure you're kind of venturing towards that, it's variable. It varies. It's a variable, it's a living system. It's a moving system, really, or moving target that you have to be able to adjust accordingly. Hence the circuits, not necessarily one arched ambient loop.
Great.
That being said, you can have circuits interact with an ambient loop. I don't want you to think it's one or the other. Okay, cool.
Another comment here. So cost of drilling appears to be the biggest limiting factor for widespread adoption of geothermal. Are there any ideas or solutions coming online to help make it more affordable?
So the ITC is big. Before, being frank, they didn't necessarily always pencil, or at least not all of them, not most of them. Now, which is why I kept drilling home the point, if you're going to be redoing your system within the building and it's attached to the geothermal system, both get the ITC. What we've seen is that is a tipping point a lot of times. And that ITC being applied to Division 23 mechanicals as part of a geothermal loop reduces your overall cost, which thereby reduces your drilling costs. But second, I will say that there's even, programs through the utilities where they'll help you with test drilling. We've seen that in New York. Con Edison took on the responsibility and the foresight of saying, look, a lot of people, like you said, want to find out if their system is worth it, and part of a true feasibility test is a test hole and a thermal conductivity test. That's not necessarily within everybody's budget, and therefore there is funding to do some of that. There's funding to do feasibility studies in general before you even get to the drilling stage. And really what that does is reduces your risk before you go into high capex activities like drilling. Drilling full systems, one of the ways you reduce your drilling costs, honestly, and this is going to sound kind of tautological, but having a good energy model and a good idea of how the system already works for retrofits so that the system is optimized and you don't have excess boreholes. That's another way. And finally, I will say some of that is on the responsibility of industry providers like ourselves. Brightcore has invested a lot in technology and in the brain trust. So the drilling cost there, it can be seen in efficient design, but also fast drilling. There's typically a turnkey solution with a turnkey price, but I'll give you a great example. There's a university on the Hudson that had us install, soup to nuts, the bore field, the trenching, the connection to the mechanical room, operation and maintenance, and the monitoring system all in one kit and caboodle. What we came to find out is that our bore field, 50 boreholes roughly, happened to be this university's green field for their graduation ceremony come May. We're drilling in February, and up in the Hudson, it can be rainy season and it can get literally pretty muddy. We were able to, because of know-how and technology, get through that pretty quickly and leave it as is and ready for graduation in time. So drilling costs, you may be a lower price point, but the time involved or the know-how or the value added after is where you typically sometimes pay the price, metaphorically. So some of it's on us. There's money out there, and there is value add. So those are the three ways I would answer that.
Yeah, it's terrific, Jonathan. Thanks so much. And that brings us right about to 1 o'clock. So I do want to be mindful of everyone's time. Anna, do you want to just remind folks where they can find the recording and the slides and regarding the CEUs?
Yes.
Survey?
Yes. We will be emailing out a survey to receive everyone's feedback. So we hope to hear your responses to that. And then we will be sending out a separate survey for anyone who wishes to receive the AIA CEUs. And I will also be sending out a link to the recording of this presentation, which will be posted on Build Green Connecticut's website. So stay tuned for that coming into your inboxes.
Great. And Jonathan, there were a couple questions, pretty technically dense ones that we didn't get to. Are you okay if we encourage folks to reach out to you directly if they had unanswered questions?
That would be totally fine.
Cool. Terrific. Well, Jonathan, thanks so much for joining us and sharing your expertise with us today. We really appreciate it. And thanks to everyone who joined and for your interaction in today's session.
Thank you so much. It was a pleasure as always. And Brightcore Energy is always here to help answer any questions. And we love Passive House. We love the Northeast, and we are true believers in this technology. So no question too dense. Let us know. Thank you so much.
Excellent. Thanks, Jonathan. We'll see you soon.
Thank
See you
you.
soon.
Bye.